Okay, welcome to all participants of our live research webinar series 2.0 under the auspices of TNC PNI Office, okay, Deputy Vice Chancellor, Research and Innovation. So our speaker this morning is Dr. Mohamad Fariz Taib from IOS, Institute of Science, with the title of Accelerating Scientific Innovation and High Performance Material Through Validated Quantum Computational Science. Before I invite Dr. Fariz to share his title this morning, to share his research this morning, allow me to share his background. Okay, so Dr. Fariz is he's graduated in physics from UITM in year 2009, and then he pursued his PhD by exploring this topic. We call it is the first principle using density functional theory. Okay, basically under his PhD work, he managed to publish about 20 papers, and a lot of his impact factor papers. All right. Then after finish his PhD in 2014, he joined UITM. Okay, and he also associate members for the Institute of Science. Okay, where he expand his research more in various fields such as batteries, supercapacitors, solar cell.
Patutlah sokong. Dia macam apa lah.
Tak dengar ke? Hello? Okay, allow me to carry on. So after complete his work, he expand his research in batteries, supercapacitor, solar cell, water catalyst, sensor, and biomedical application. So he graduated a few PhD students already, and currently he supervises many PhD students. And he also have an active collaboration with CIRIM, UKM, UTAM, UTM, and UPNM. So I think this topic is very interesting. So without further ado, I would like to invite Dr. Mohamad Fariz to begin his talk. Dr. Fariz, is you ready?
Okay, ready.
Okay, please, you may start. Thank you.
Okay, Bismillahirrahmanirrahim. Alhamdulillah. Assalamualaikum and good morning. First and foremost, thank you to the chairperson, also actually my former PhD supervisor, Associate Prof. Dr. Oscar Hasidino Hassan. Thank you to Prof. Nazib Suratman, TNC Pendidikan dan Inovasi, organizer committee for this webinar, Sofina and team. Institute of Science, under Prof. Zurina and Associate Prof. Dr. Zuraida, because give me this good platform to share my research project. And all audience, maybe inside or maybe other outside UITM, thank you for participating this webinar. Okay, before I go further my presentation, I want to introduce again myself. My name is Dr. Mohamad Fariz. I'm a member of Institute of Science under Center of Functional Material and Nanotechnology, FMN, under head Prof. Rusub and Prof. Dr. Malik Marwan. And I'm also a senior lecturer at Faculty of Applied Science. Okay, today's session I will share a little bit about my research work related to my experience on PhD and now what I'm doing about the quantum computational science. And I choose this title, actually the Accelerating Scientific Innovation and High Performance Using the Quantum Computational Science. And I try to explain how by using this quantum, actually we can accelerate our scientific innovation or maybe to design a new material for future. Okay, hopefully all of you can hear my voice and see my slide clearly. Maybe Dr. Oscar can respond. Can you hear my voice?
Yes, Doctor, I can hear.
Okay, thank you. Okay, this is my content overview. Firstly, I will give the introduction to the quantum computational. The second one, of course, we need to know which theory behind the quantum computational. I will explain about the quantum density functional theory, and also the computer code software that are available that researcher or also industry can use. The third part is very important because this is the step when we did the computational method or step. I will explain step by step, and then also we can see the current or trend publication related and industry demand related to the computational material science nowadays. And also we offer or we share to all of you about the UITM computational facilities, what we have, the hardware and software. Also, I will explain, I select a topic to share to all of you. And also I will introduce my research group and our collaborator. Okay, we go to the introduction to the quantum computational. Okay, this is a conventional approach. Most of us need to synthesize and maybe prepare the material before we get a good structure of material. And then we proceed with characterization and support the technology demand. And now way forward, we're using the computational approach for the first beginning our step. And then the rest is similar with the conventional approach. Okay, actually, of course, the computational and experimental is complement each other. We need to support computational. We need the computational to support the experimental. Also, we are the computational need experimental to validate our calculation. Okay, actually, what is the computational material science? Okay, computational material science is computer programming using the quantum, either physics or chemistry, to calculate the properties of material. And widely used in condensed matter physics and material science in order to understand, predict, and interpret the experimental result and investigate at the atomic level part. Most of the researchers under the material science, computer and material science, interest in several topics like condensed matter physics, computational material science, related to solid state material science, nanoscale, polymer, and interface material science. After this, I will show some example related to that topic. And actually, we interest to looking for study the basic or origin of material. I think nowadays this is very important if we want to publish our work, especially in the experimental. Some fundamental demand from the paper we need to explain a detail some fundamental or basic how and what happened to our material actually. And by using the computational, maybe it can assist some of experimental work to explain at the atomic level. And the second one, this is a type of study we can investigate the stability, structure, defect, or maybe new mechanism in material. And the third one is very interesting. We can design a new material or novel material. For example, my PhD work before this, I work on a thin titanium. Actually, last 10 years, experimental have a challenging to actually stabilize the tin, because I want a tin 2+, but when we sintering the tin, sometimes tin can be 2+, 2, 4+, difficult to control at that time. That's why we know tin have a new good potential. We try calculate using the first principle or computational, and then we can give the prediction good properties for that material. And nowadays, some of researchers can synthesize that material and refer back to our theoretical work. Also, in advance, some group of computational or theoretical can introduce a new technique of initial calculation. Okay, we can see the material modeling technique. At the top, we have a quantum mechanic. Of course, from the figure, we can see clearly that material modeling technique at a quantum level is most accurate compared to others. However, when we deal or working using the quantum level or atomic ground state, of course, the computational cost also increase. That's why to perform computational material science, we need high performance computer or high speed computer to run our calculation. Another thing, when we we want to perform the calculation at a quantum level, the limitation of number of atoms also we need to consider. We need to avoid number of atoms more than 100 because it can take more time, and sometimes your hardware or computer cannot support your calculation. And maybe we can use several techniques like primitive cell calculation and others to ensure that our calculation can be done. Okay, this is advantage. I got this information directly from the Material Studio website. Actually, one of the software that we use in computational material science. The advantage, the first, of course, similar with my topic, can accelerate the innovation process because we can drive deeper understanding of the interaction that define the material properties. Of course, nowadays, the cost is very crucial or very challenging to all the researchers. By using the pre-screening, we can reduce the R&D cost actually. We can minimize the number of physical experiments via the virtual screening candidate. Of course, when we're using the computational, we can get the higher probability success. And then, of course, we can synthesize based on that direction. And then we can get the good result for our real experimental. And the third one, improve the R&D efficiency because you can share best practice within the pipeline pilot to reduce a non-value added task. And then, like I mentioned before this, the complement laboratory experimentation with powerful material informatics. This the procedure we can see from the figure. We have the data input using the Schrödinger equation basic. We can get the FT output, and then we get the property descriptor. Okay, the number one, the calculation require input. Of course, we need the crystal structure, atomic position, and so on. And then we need to choose the right approximation in the DFT and numerical convergence parameter. Okay, to the researcher, maybe some researcher know about the DFT. Very important to make sure that our parameter is converged, the input parameter before the calculation. Okay, the output, of course, DFT can give the output based on the such as electron charge density, total energy, and optimized crystal structure, and also band gap. Then lastly, the fundamental output from the DFT we can analyze or combine to produce descriptors relevant to a given application. Okay, then we talk about the theory. The second one, the theory that we use or implement in the computer code software to perform our calculation. We use a well-known theory of quantum, that is a density functional theory, and I also will share about the computer code software available to use for research industry. Okay, actually this DFT theory, I just share the basic or general knowledge about the DFT. DFT is a quantum mechanical method for solving the electronic Schrödinger equation of molecule and crystal using the formalism that is based on the charge density rather than the wave function. The simple word is before the DFT developed by Watercone, researcher introduced Hartree-Fock theory based on the wave function. But the wave function base to calculate the total energy is very complicated or complex. That's why it's not suitable to, especially to calculate the total energy for the many body system. That's why the Watercone introduced the DFT. They try to calculate the total energy of the material using the charge density. That's why from there, the development or the revolution of the computational material science can further can the number of researchers involved in computational increase because the success development of this theory. And also he got the Nobel Prize 1998 because of the development in DFT. And Alhamdulillah, I got the good opportunity. Thank you to UiTM and Academic Science Malaysia because for the financial support to attend the Lindau meeting. I go with another 5 young researchers in Malaysia. And then Academic Science give us opportunity to interview 3 Nobel laureate, Nobel Prize winner, and I request to Academic Science and Team Malaysia to interview Watercone, and Alhamdulillah, I got a good opportunity, good experience to interview, 1 hour interview with Watercone actually. And then actually the sad news, Watercone passed away, I think 4 or 5 years ago. Okay, this the basic, the general concept of the DFT. I will not touch further about this. I think you can read by yourself. I just give just overview. Okay, these are the main theory under DFT. We have the second theorem. We have the Hauenberg-Kohn theorem. The second theorem, the Kohn-Sham theorem, and then the below. This is the most important equation. Okay, as a scientist, or maybe I give a general for the all. Actually, the basic DFT. We can see on the left. We calculate the total energy based on the kinetic energy of electron, potential energy electron, potential energy between electron and proton, and this is the novel DFT success because of the exchange correlation. They introduced the exchange correlation energy. That's why we have the NDA or GGA. And of course, if you're interested in this area, you should know basic about the DFT, and you can get the information, I think, available in the website. So many reference book or slide related to the DFT. Hopefully after this, you can search about the DFT because I just give the brief about the DFT. And of course, like I mentioned before this, DFT have kinetic, potential, and exchange correlation. At the potential, we have the different basic set. For example, we have the plane wave, Gaussian or numerical, and others. Okay, actually, the most researcher based on the computational methods are using the plane wave. Okay, and we at UiTM have the step and computer code. Actually, what is the simple concept of plane wave? Actually, the calculation using the plane wave, we deal with, we treat only valence electron. Okay, if you want to modify your structure, for example, you can using your pure structure and you doping or you modify, of course, your properties will be changed. And it affects actually at the valence part. That's why the most of material design or calculation using the plane wave rather than others. But the second one, I think the important is a numerical. We also have a D-mol cube. We calculate using D-mol material like graphene, the 2D structure. For example, we want to see the interaction between graphene and others gas sensor, for example. we deal with two different elements. That's why we're using the numerical part compared to the plane wave. Okay, this is the list of specification of DFT software package. Of course, some of us ask either we have the free software or not, or what the status for our custom and demol. Okay, we can see here some material, some computational software using the DFT are free, like the Abinet. We also have a Quantum Espresso, Siesta, but what we use custom is free for UK, but commercial for others. The market also commercial. Okay, why we buy the custom and not use the free? Actually, in other countries like US, the syllabus of DFT have include in their degree level. That's why they have a good advanced basic for solid state or computational quantum. That's why there no need to use the commercial one. They're just using the free because, of course, if we buy the commercial, we can get technical or maintenance support from the developer software or scientist software. If you have faced any problem, we can ask them to help us. Especially we are in Malaysia, we are limited knowledge on lack knowledge on the advanced computational. We need to learn from the basic back, and of course we need to support from the developer. That's why we choose to use commercial software, custom and demol cube. Actually, this idea we got our group got the idea. Professor Zahan, Dr. Oscar, and Prof. Malik got the idea from the National University of Singapore. We visit them 2008, and then we got the idea to start the computational in Malaysia, or in UiTM. And then, of course, as I mentioned, the basics, different basics. Actually, when you start using the computational, you need to see your origin work, origin material, what you try to achieve, or what you try to get or calculate from your research. Different material, different treatment of basis set. Okay, the most important, I think, as I mentioned before, this about the computational method. We can see the step of the computational. Okay, first step, modeling the structure. Okay, actually, this is very important. First step, we need to ensure that our input is the right input. You need to know the basic. Because I share the crystal base because my work on the crystal base. Some others work like I see Dr. Fatima work on maybe different structure. But my group work on the crystal structure. I share based on the crystal. Okay, actually they have some perception. Some researcher, experimentalists, they said if we want to draw the structure, do you need the experimental data? Okay, actually this not totally wrong, but actually for input data, we have 2 or 3 several methods. For example, we can directly import the crystal database using the C file, and then also you can create or draw your own structure. Actually, you have if you have the basic advanced knowledge on the crystallography, you can draw by yourself. No need the input from the experimental. Actually, that's a type we call the ab initio method. And then, of course, the most famous method, we give or we draw the input data using the SRP refinement. That's the most famous type of method to drawing the structure based on the experimental. Sometimes the researcher, the report in a paper, both experimental and theoretical. That's why they're using the input from the experimental. And then we need to optimize your structure. Okay, they have a rule of thumb here. garbage in, garbage out. That's why you need to ensure that your structure input is right. And then, of course, after you drawing by yourself, after you got the C file and maybe you give input data from experimental, you need to optimize first. After the optimization done, your bonding, your lattice parameter, your volume already optimized. And then after that, you can proceed to the next calculation to get your property that you want. For example, band gap, electron density difference, and also after you finish your calculation, you need to analyze your data. Okay, for the first step, as I mentioned before this, in Malaysia, especially we are in our group, we need support from the visualizer. Actually, we also have the famous free software visualizer, I think Vesta. But for us, we already bought the Material Studio Visualizer. Okay, you need to, they have a different, Material Studio Visualizer is not a quantum based, this only for the drawing the structure. Okay, using the visualizer, we can sketch the atom, sketch ring, fragment, create control, clean, adjust hydrogen, modify element, and then we can build the polymer builder, analog builder, nanostructure, transport device builder, method structure, crystal builder. Crystal is our work, crystal builder. And then, of course, if you work on a surface and layer, you can use the surface and layer builder. I will explain a little bit about this part. Okay, we go to the sketching and editing structure. I just draw the example benzimide molecule. You can see, you can draw. You need to create 3D atomistic document first, because all the structure we deal in a 3D X, Y, Z exists. And then you can draw, you can choose from the periodic table, sketch the oxygen, nitrogen, and then you can get the benzimide like this. Okay, for the researcher background of polymer, you also can work on polymer. You can see we build the polymer, for example, the homopolymer. Okay, of course, if you have a good background in polymer, you should know the basic input here. You need to know the basic input. I'm not the background polymer, that's why I'm not familiar with this. But I just show the ability of this software. Okay, this is an example of a PMMA polymer. Okay, this is a crystal builder. I give an example how to build the zinc oxide. First step similar, create the 3D atomic document, and then we draw the big crystal, and as the crystal player or researcher, you need to know the basic about the space group, crystallography. You need to know the lattice parameter, the angle. For example, when you deal with monoclinic, pentagonal, cubic, is a different, of course, different the lattice and the angle you should know. And then, as I mentioned before this, you can get the data from the crystallography open database. And of course, you can get the information from the other theoretical work from the publication. We can see the input, and then we also can draw from the input others publication. Okay, here, for example, we start using draw the lattice, and then you need to add, for example, zinc, add an atom zinc. You should know the position ABC, and then we can see the zinc appear here, and then you add atom oxygen. Now we already get the zinc oxide, and then of course this is the only first step. After this, we need to make our optimization first before we proceed our calculation of the properties. Okay, this is for the person who work on the nanostructure. Beside the CNT, we also work on the graphene. These are how to build the single wall and a multi-wall nanotube. Also, similar, we need to know the NM, the parameter, the carbon, the bond length for the carbon to draw all of this. Of course, researcher background, the CNT or graphene know about this. Okay, this example structure, we have a metal oxide, MgO, TiO2, and others. The example for the ceramic, we also have a glass, very difficult to handle the glass. And also we can draw in the polymer. Just an example, I think we have more compared what I show today. Okay, actually, what are the features and capabilities for this software? The calculation task, we can calculate the total energy, very important task. Optimize our structure, we can optimize the lattice parameter, volume on bond length. Also, we can run the molecular dynamic and elastic constant. We can get the bulk modulus, shear modulus, Young modulus, and Poisson ratio. Also, the transition state search. Okay, and then this the list of properties that we can calculate: band gap, band structure, residual state, core level spectroscopy. You can see the electron localization, electronic excitation. Okay, this optical property is very important for example, the person who work on the material based for application photocatalyst, or maybe water splitting for fuel cell. Also, you want to see the optical properties. We can get the reflectivity, loss function, dielectric function, refractive index, and absorption coefficient. Also, if you interested to see to investigate the phonon vibration, you can run using this software, computer code, and population analysis. Okay, next we go to see what the current trend publication related to the computational material science and some industry demand of the computation. Okay, we can see the publication. We search using three different terms. First, we search DFT. DFT is the theory that we use, and then the second one we search CASTEP. CASTEP is our software that we use, and then we search the first principle. First principle is actually the method. If you read the title, start with first principle, actually we know that the first principle, the calculation using the DFT-based theory. Okay, we can see the trend increase every year, 15,000, almost 16,000 publication on DFT 2019. Also, the similar trend to the CASTEP and the first principle. That means we know that nowadays we under Industry 4.0, of course, we need to rapid or to accelerate our research. Maybe I think the two important part is try to accelerate our research, and the second one, we need support on the fundamental how and why our material happen after we modify it experimentally. I think that's why the number of publication related to the FT and computational increase year by year. And of course, if you are a researcher, you try to find a new or try to design a new structure. This is most of the famous modification that we can do using the Material Studio, our software. We can co-doping or doping our pure material. For example, this is zinc oxide. You also, most of the researchers also work on the surface, public and RSC Advanced about the surface. The third, interstitial defect for gallium, aluminum arsenic. And then vacancy defect, some of researchers study on defect. These are famous for the graphene. We also publish in surface science, impact factor 4.8, I think, adsorption, very famous one now, especially for the graphene. We investigate the adsorption, interaction between elements, for example, gas, for the gas sensor. We want to see the efficiency or adsorption energy. between two material. And then also researcher study on interface, the idea of the structure modification that we can done using the computational. Okay, these are the just show the selected publication related to the first principle. We can see the term of first principle study, except in the scientific report. As I mentioned before, this high impact journal now demand their need the fundamental to explain our result, especially in experimental. That's why I think nowadays the computational necessary for high impact publication to explain, to support the experimental data. And then this example for water catalyst, also we can also investigate on thermodynamic, example paper. And of course, outside at the university, they have their own theory and computational group. We can see University of Surrey, Duke University, Imperial College London, Glasgow University. They have their. So this is just several. MIT also have their group computational, and hopefully our group can create one group computational authentical under iOS, inshallah. And then of course we try to stick together, collaborate with others theoretical and computational player outside UiTM and in UiTM to maybe to create the theoretical and computational simulation group in Malaysia, inshallah. Okay, of course, the demand from the technology or industry, the computational can support the pharmaceutical, chemical energy, automotive, aerospace, biotech, consumer packaged goods, electronic or engineering. Right? These are actually the some of industry that use similar with our software actually. The global player industry, they try to accelerate their production or the design, the new high performance material using the quantum computational. Petronas Chemical also one of the user for this simulation. And last week I got news to group on R&D Petronas called me to make a discussion about this computational material. Hopefully after this we have a connection with industry between university and collaboration between university and industry, inshallah. Okay, I want to show the UiTM computational facility, what we have, and I present a little bit about my research work. Okay, we have, of course, I mentioned before, when you deal with the quantum-based software, or you want to calculate your calculation using the quantum level at ground state, we have a Material Studio software. We have a perpetual lesson, podcast step, and the molecule. For perpetual, of course, the price above the 100,000 per lesson. And we need support using the hardware, high performance computer. We have 18 core and we have the 24 core. Of course, we open to the collaboration or open if all of you interest to work with us, especially in with UiTM. We welcome to all of you to collaborate if you need some maybe collaboration related to the computational. Okay, this I choose two topics. I just show the ability and my PhD student, and actually this with my Prof Malik PhD student. I co-supervisor for this student. Now Dr. Hazri is our postdoc at iOS. Okay, their work actually they investigate the material-based TiO2 for the SLC solar cell. We can see the demand from the PSC. We're talking about the efficiency. And then, okay, actually what are the problem from this research? Of course, we know the wide bandgap of TL3.2 causes a low absorption for solar spectrum, only for 4% efficiency at UV. That's why we try to modify to get the good range for TiO2 based material for this case. And also, photoquantum efficient is very low because the photoexcited electron hole pair tend to recombine easily. That's why the objective to evaluate the structural, electronic, and optical properties, as I mentioned before, this is the fundamental part is very important to modify our material or to design advanced material. That's why we start with the structural and electronic first to see the way how we can get the idea how to modify or enhance our properties. The second one, to calculate the phase stability, if you deal with the crystal structure, of course, with temperature, your structure can change. Your phase structure will change. For example, from tetragonal to cubic, maybe rutile, anatase. That's why you should know which structure is stable at a room temperature. For example, for TiO2, we know experimental already mentioned, but we try to investigate using the first principle. And also to modify, we modify with doping with lanthanide, dot CE, ND, and ER. Okay, we can see this the first step for the calculation. After we optimize, we can get the structure parameter. We have a lattice, we have the volume. Okay, there are 2 or 3 steps because I got many questions from the researcher or experimentalists. They ask us, how do you know your work is accurate? How you ensure that your calculation is acceptable? Okay, actually, by doing the DFT calculation, after you get the data, for example, the lattice parameter, of course, we have 2 ways to ensure that our calculation is acceptable. First, we validate our calculation with the available experimental data. The second one, we also can verify with other theoretical software. For example, we use maybe we can verify with others, for example, VASP. That's why they have no issue, PhD or master student using the DFT or computational need to support using the experimental. If you can do that, it's a good for the research. But actually, if you were on totally using DFT, also you can done your master or PhD, because we can validate or verify our work. And of course, if you work on DFT, a lot of things you need to know before you get the answer. It's not easy like you click, you get the result. No, that's a wrong perception, because this we deal with quantum based. We should not deal using the quantum or modeling, simple modeling. This is a quantum based, so we need to ensure any parameter before we publish our work. And again, we can see the percentage different. I just present the concept. I'm not interested to explain detail about my finding. I just give you overview the ability that this method of study can give us. Okay, this phase stability, you can see some calculation DFT. Of course, I know there are also have underestimate or overestimate calculation using the DFT. For example, for this calculation, when we calculate the stability structure without correction, we call the potential correction. How about you? We can get the wrong result. Okay, the first way without you disagree with experimental due to the drawback of DFT on this calculation. Of course, you should know if you were on TiO2 or zinc oxide, for example, you should know that either you need the correction or not. Most of the paper or publication already mentioned about this. Just follow the literature. And also your expert or maintenance service, like I mentioned before, every developer, they have the scientific support, professor or scientific support. We can ask them either our procedure is right or not. And then after make a correction, you can you get the right actually phase stability in the end of after you apply your correction. This is a more technical issue. You should learn slowly about this. Okay, we can see here just simple. I think because most of the audience is not the totally background on material studio. Computational material. That's why I just show you the general part. You can see the pure. We have a lattice parameter ABC and volume. The pure TiO2, and after we doping, we can see the different the changes. Of course, changes. It can change because we dope with other element. We can see the different what happened after we doping. And then, of course, it will affect the properties. That's why I said using the computational, we can explain how and why it happened. For example, if you work on the experimental, you doping and then you make a characterization. Of course, you got the changes characterization, for example, band gap and so on. And to explain how and why, I think we can use this type of method to complement to explain the fundamental part at an atomic level actually. Okay, this for example calculation for impurity formation energy. From here we can see how difficult the element can enter in the pure TiO2. We can calculate, we can see 1.17 electron volt for CE dope. That means CE dopant is easy to incorporate into TiO2 compared to NP and ER. We also can get this idea. And after this, we talking about the position of dopant. This is just a general simple doping for TiO2. And of course, after you doping, of course, the electronic also change. We can see the band structure different with a different dopant, and also we can see the gap. Okay, here we have a two term. First, structure, electronic structure. The second term is electronic band gap. Different actually. The structure, we can see the structure, and then the gap just focus on the gap of valence and conduction band, between valence and conduction band. Okay, of course, the band is the localization of electron. We can see the line. The line is actually represent the electron. And then of course experimental also can get the value of band gap, but which state of electron contribute to your band gap? That's the point. We can explain using the material studio. Okay, here we can see the gap, and then this is the powerful result for density of state for our computational material science. I not compare with experimental. Sorry, I just mention about our work. This part is very important for us, crucial result. Here we can see the contribution of, we're not talking about only the general element like a CET. I know we give the information about the specific state of electron. For example, here we can see here dominated by oxygen 2p, and on the right side valence conduction we have a titanium 3d and CE for F. That's why I said that when you deal with the plane wave, we only treat the valence electron. Valence electron play the main role to the properties of our matter. That's why at the top we can see the total density of electron, the localization of electron, and we can see the detail at the below. The detail we separate. We call the partial density of state. We separate every element using the different graph. We can see the clearly contribution of the element after you doping. Okay, when we work on the AC solar cell, of course, the most important is the optical part. We can see we try to improve the performance efficiency at the visible range. Here we can see pure and after doping, we can see The dominant at the visible is the ND dot. And the second one is CE dot. And then we have ER and pure. After we doping, of course, all the efficiency or absorption range increase. That's a good sign for apply for the solar cell application. And then we can, for example, if we see here, our calculation clearly show that ND dot is dominant in visible region. And after this, we can further our study. We can various our weight percent of ND. Different weight percent ND to see the optimum weight percent of dopant can give our maximum good performance for at the visible range. I think I already explained similar with this conclusion, and Alhamdulillah we published more 5 to 6 related to TiO2, but I just show the result in physics and materials express for TiO2. Okay, you can see the title, how about you calculation using a 3D method of TiO2. How about you is the correction. That's why this a very good paper in 2020 already cited by more than 12 citation for this, only for 2020, because most of the researcher or work on computational need the correction, the right parameter actually. That's why the paper based on the correction is very famous now, DFT plus U and so on. Okay, this is very interesting. I collaborate with the mechanical engineering UITM, Dr. Hussein, work with Dr. Oscar. We actually have one student PhD work on the first time we go to the biomedical application bond implant. Actually, this about the titanium alloy. Okay, of course we know that titanium is very good for implant, but the problem is the pure titanium, the range of the Young modulus is high, 113 GPa, but the human bone is between 10 to 30 GPa. Of course, titanium have a good advantage, but they have also drawback, very high Young modulus. But we can overcome the problem with a doping. Or alloying, use we call a beta stabilizer to reduce the alloy Young modulus. That's the idea. I don't go deep on this. Just show the what we done using the first principle. Similar electronic properties. This focus more to the, of course, the mechanical, because we want the final output, we want the titanium alloy with in the range, Young modulus in the range of the human bone. Okay, this I want to share to all of you about this. This is very very important. If you want to alloy or doping at the which position you want to dope, because some maybe we have a 16 place to dope, and which part. Actually, using the calculation DFT, we can calculate the total energy or cohesive energy, and then the lowest energy is the best position to dock. That's why we can see different position. Okay, from this we also can publish. Of course, these are very good result for others to refer for the future. Different dopant give the different position of dopant. We also can give the have some theoretical or atomic level view to the experimental to deal with the titanium alloy. Okay, these are the third dopant. Okay, here we can see with different doping with different element metal. We have different weight percent. We can see the lattice or volume. Here our result from my PhD work, my PhD student. Okay, also we can see the detail. We're not talking about the Young modulus only. We also see the detail of the C11, C12, because these are cubic, C44. We can see the human bone here. At the last structure, we can see which alloy or dopant can give close to the human bone. Of course, these are only the first or second step. We need to further investigate about this matter. Okay. Lastly, I want to show our research group and collaborator. Our member, I'm Dr. Mohamad Fariz. My supervisor, Lieutenant Colonel Prof. Dr. Mohamad Zahra, now TNC at UPNM. Thank you so much, Prof. Zul, introduce us about DST. Also, Professor Associate Prof. Dr. Oscar, my PhD supervisor, Dr. Malik. Thank you so much for your big contribution in our group. And of course, I'm with my good friend, Dr. Mohamad Kamel, together try to enhance our group, maybe contribute to UITM or others, maybe to have some experimental to support some experimental work from our collaborator. And Alhamdulillah, complete PhD under this group start 2008, 2009. 7 PhD student and 5 master student. Now in progress, we have active 20 PhD student and 15 MSc student. Also, we collaborate with other team outside UITM, Associate Prof. Dr. Azmin, Material USM, Dr. Ashadi from UTM, Prof. Azhan Hashim from UITM Pahang, Dr. Usim from Mechanical Engineering. We also support a team from High COE, from IMEN, Prof. Dr. Amri, Material Group, Prof. Dr. Associate Prof. Dr. Norisan kami UKM, also team from UPNM, Dr. Fadru Wafi and Dr. Zulaika. And actually, we got the idea from Prof. Luli, National University of Singapore. They start the 2000. I'm not sure. We go to visit Prof. Luli 2008, 2007, and then we got the idea to bring to UITM actually. And then we actively collaborate on paper and work with Dr. Batia Ul-Haq, Dr. Amiruddin Shari, UTM, Associate Prof, sorry. He a very nice person, help us, especially in the theory side. Dr. Amiruddin is very expert on the quantum and DFT in UTM. And we have a good new friend, Dr. Fadil Fasihi from UNP. And then we collaborate with UM. UM also asked us to make a collaboration and help them to support the experimental data. We are student not admin. UTM KL also, we have one student PhD collaborate with us. And of course, in UTM, we have Dr. Fatima from the chemistry, Aurins, Prof. Rohaya, and hopefully we can collaborate in physics and chemistry, because some of my collaborator demand need material, organic material or polymer. Maybe after this we will collaborate with them. I think that's all for me. Thank you very much.
Okay. Thank you, Dr. Fariz. Very interesting talk. So are you ready to take any question from the audience, Dr. Fariz?
Oh, okay.
Okay. And then I would like to open a question from audience to seek some clarification from Dr. Fariz. Anybody, please? Check on the chat. We have some question. We have from Dr. Sufri. Yeah?
Okay.
He asks, could we analyze the properties between interstitial doping compound and substituted doping compound using computational study? I repeat the question. Could we analyze the properties when we do the substitution?
Okay, good question. Okay, I back to Okay, I try to answer the question. Thank you for your. Maybe we can refer back. Okay, can refer back to our slide here. Okay. Okay, actually, to answer the question from the Dr. Sufri, okay, we can see here. This example, interstitial defect. Okay, some researchers work on the interstitial and some work on the doping. Of course, when we deal with the different type of modification, we need to know the fundamental first. Of course, the doping or substitution different with the interstitial defect. Some researchers try to make the calculation interstitial, but the calculation is failed. This is because we need to set when you deal with a different modification. Of course, interstitial is very hard to calculate because the element is not attached at the bonding. But of course, we can do the calculation because most of our application work on interstitial also. But you need to know because different type of modification you need to deal with a different parameter or procedure. Actually, they're possible to calculate. Hopefully, I already answered your question.
Okay, thank you, Dr. Fariz. Audience, any comment or question? So there is a comment from Dr. Siti Fatima. Let me read here.
She also a player on DFT.
Dr. Fatima Salim. Okay. She commented on the use of experimental data. Because we are doing on solid state and on liquid state. I mean, what she commented here that we need to use or acquire some experimental data to support, especially if we are doing on the liquid state. Maybe Dr. Fadil can have a look at the comment.
Okay.
First of all, we thank Dr. Fatima for the comment.
Okay, very good comment.
Can respond.
Actually, as I mentioned before this, they have. I will not say that totally wrong perception. Actually, just a perception. Actually, we have 2 or 3 ways to get the input data. For example, some data you need, of course, when you deal with a liquid base, or I'm not sure because I'm the crystal material background, and of course, in our work in crystal, some material not available the experimental data. That's why we need to know the F1 crystallography background. And then actually for the crystal only, I comment only for the crystal background. Actually, we can draw the crystal without any data from the experimental because if you learn advanced crystallography, you can understand what I mean. Actually, the lattice, the hexagonal, the space group of the crystal is already fixed or well known. We just put, for example, add the atom and set the position of ABC, and then you can get the atom will attach automatically in what we call periodic type of the attachment. If you just put the one, for example, position of atom, it can automatically attach the atom at the group of periodic atom element attachment lah. That means the conclusion is actually we have 2 or 3 method for the input data, not totally depend on the experimental because as I share to all of you about my PhD work about the thin titanium. Actually, thin titanium is not yet synthesized at that time, 2009. And then we got the idea this material have a good potential to replace lead in PZT. That's why we run the calculation using fully DFT without any input from experimental. And then after this, nowadays, 2019, 2020, after their success to synthesize that material, thin titanium, most of them cite our paper or refer our paper to compare their result also from with our theoretical. They can be a two-way. If you have the experimental and then you run the calculation, you can validate your calculation with experimental. If you done your theoretical or computational first, and then after that, the experimental success to synthesize the material, the experimental can refer back to theoretical to make sure the both theoretical and computational are in a good agreement. I think, and last I want to add different way of the DFT or computational material, different deal. For example, Dr. Fatima maybe have a different different material. I'm also not familiar. That's why one of my collaborators asked about related to Dr. Fatima, and we need to help from Dr. Fatima because I'm only work on the crystal work material. Okay, that's all.
Okay, thank you, Dr. Fariz, for the response. We have more questions from the audience. Okay, while waiting for the audience to respond.
Okay, thank you.
There's a question from the chat. Two questions. The first question is for doping. Can we extract the information regarding an atomic distance for each element in our crystal structure?
Yes.
Okay, yes. Okay, thank you, Dr. Fariz. And the second question, what is the difference between position of atom that you showed just now? I'm not sure what it's referring to. But the following question, what is the factor the result give different value in potential energy? So,
okay.
You want to respond on this? Or?
The last question, though, you're talking about the potential energy on the correction. How about you? Maybe the question about the how about you, I think, because we talking about the potential energy correction. Okay, actually, for example, if you run your calculation without the correction, some material, the FT fail to identify the localized of electron. That's why some calculation will give the wrong result on the electronic, for example, band gap or band, not the band structure, tapi maybe band gap, because they are difficult to identify the localized of electron, for example, for zinc oxide and TiO2. That's why the potential correction, how about you, necessary, are needed to add in the calculation of pure DFT. We have, for example, we have LDA and GGA. We need to plus with LDA and GGA plus U. Okay, of course, we don't know how much we need to run a different range of the U to get close to the experimental. This is very important. If you get the right correction, for example, potential U, close to the experimental, you can use that parameter for further your calculation to the others properties. That's a very important step. And then I'm not sure about the. Can you repeat, Dr. Oscar, the question about the position electron?
What is the difference between position of atom that you showed just now? This is the question, but did you get it? I mean,
I'm not clear because
to any of the slide.
I'm not sure because I just give the general maybe comment. Actually, in a crystal material, the position of atom is we need to know the FCC, BCC basic for lattice or material or position. I maybe if you open the crystallography book or reference, the position of atom, we can, if we know the position of BCC or FCC, for example, we just put 0.5, 0.0, you can get the right position for your atom. That's the basic, because the lattice only deal with the BCC, FCC like that, the origin of atom position. I think just a general, I only can respond the general about the position.
Okay, I think we have a last question from the audience, Dr. Fariz. Can we calculate surface energy and predict the crystal growth?
Okay, this actually the recent study using the FT actually based on the surface. Many researcher computational medicine can do the surface study, because surface study we need to consider a lot of things. I'm not sure because I'm not work on the surface. I just have experience on the graphene, just absorption energy. But you can get the more detailed information from the literature. Of course, many nowadays the recent study, most of the researcher focus on surface study, and then you can read the literature and you can see actually which parameter or the method that they use to control the surface and what the property that they can get from the surface. I think, of course, when you deal with surface, of course, the energy is calculation of energy very important.
Okay, I don't know how much time that we have. Are you willing to take more questions, Dr. Fariz?
Okay.
Okay.
Yes.
Okay. All right. Then I just read another question from the audience. Normally, experimental see when go for doping concentration, then electric conductivity changes. So for computationally, same way, vary doping constantly to see electrical conductivity. I'm not sure you got the question, Dr. Fariz.
Okay, I just
I think he's answering. He want to see the effect of doping to the electrical conductivities, maybe something like that. Can we see from the computational?
Okay, actually, they have a two part. First, experimentally can varies the weight percent of doping by calculation of the chemical equation. I think the calculation of mole or something like that, and then they get the different weight percent to synthesize the material. But by using the computational, we can calculate the weight percent by the number of electron or element. And as I mentioned before this, the position of element, we also can know actually which part, if you doping 1%, 2%, 3%, which part the substitution or dopant go to the site of element. We can see by calculation, we can investigate or prove by the calculation of cohesive energy. We can see which part give the lowest energy for the calculation. And then, as I said, after we doping, to give the overview to the fundamental or explanation to the experimental or our project or research. After you doping, we can see which element contribute to the property. For example, band gap. We can see the contribution of element. Okay, for example, this part. Okay, this we can see the dopant. We can dot with a different dopant. We can see the formation energy. Of course, we got the different properties after we doping. For example, band gap the change, and then the important is why the band gap change. We can get the information, and then the DFT or computational can explain in terms of state of element, contribute to the changes of the properties of electronic, for example. Of course, the optical also we need to know what happened after doping. This is the key or the most crucial result for us, the city of state. We can see what happened after doping electronic based on the electron contribution. Okay, hopefully I answer that question.
Thank you, Dr. Fariz. I think we take one more last question, Dr. Fariz.
Okay.
It's a very interesting question.
Okay.
What is the difference between CASTEP and other software in terms of calculation of crystal structure?
Crystal structure?
Yeah, difference between CASTEP and other software in terms of calculation of crystal structure.
Okay.
Maybe he want to have a comparison between CASTEP and other similar software.
Okay. Actually, first, of course, are different between potential or basis set. For example, we have a Gaussian, numerical, or plane wave. For example, at the same basis set, CASTEP and VSP, of course, the developer or scientists are different. For example, I give the analogy just, for example, a tire. We have a similar use of the tire in car, but the different type of tire gives a different price. For example, this software, we have a CASTEP VSP. Of course, they have a different basis set, but some we call the approximation. For example, local density approximation and GGA, the exchange relation of the functional may be different using the different CASTEP and VSP, for example. That means different software they give different functional or mungkin function or maybe properties, ability or features property that we can calculate. For example, if you run band gap, similar property, for example, band gap for CASTEP VSP, we need to see what type of functional they use. Of course, if you use the similar functional, your calculation should be close between the both. Even different software, you should get the close result for the calculation.
Okay, thank you, Dr. Fariz, for the talk. And
Dr. Oscar, I want to add one more before before we end our session. Actually, actually, I'm here. I'm not talking about computational is better or the experimental. Actually, we try to show what are the ability of the computational. Also, we want to support or contribute, collaborate with the experimental. Of course, both experimental and computational are important and complement each other. That's all, Dr. Oscar. Thank you. Thank you to the NCPI office for this good opportunity.
Okay, thank you, Dr. Fariz. To all UiTM staff and lecturers, you can log in your training via the link given in the chats. And for those who would like to contact Dr. Fariz, you may so via emails to have further collaboration. Boleh ya, Dr. Fariz, insyaAllah?
InsyaAllah, okay.
And I think we can close this talk then by thanking the Office of Deputy Vice Chancellor Research and Innovation and for giving the opportunity to share something about these computational materials. And then I know we are in a PKPB, so I would like to say thank you and stay safe.
Okay.
I think we can end this. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Thank you all. Goodbye.
Thank you, Dr. Oscar. Thank you, Sofina.